What we're going to be going over here is multiple linear regression, and we're going to look at multicollinearity model testing. But before we get in testing our regression model here, we'll get an understanding of what we're talking about when we're talking about multiple linear regression. Okay, so starting out with an XY graph here, we're going to have three different sets of data points that we're going to be looking at here. And along our x-axis, this is where we have our independent variables, and we're going to look at three of them here, x1, x2, and x3. And when we're talking about multicollinearity, this is when two or more of these independent variables that you'd be testing here or measuring measure really the same thing. And what you end up having is standard errors in your regression model. And when we're talking about these independent variables here, these independent variables here, x1, x2, and x3, are really going to predict our dependent variable here, dependent y here. Okay, so let's look at those three different sets of data that we're talking about here. So first, for our blue line, those would be our blue circles here. And I'm showing each of these lines where we regressed those data sets here separately against our y dependent variable here. And this solid line here, this blue line, when we regressed it separately here, just looking at, in this case, it's a independent variable x2 here, we came up with a certain linear regression here, or slope of our line here, 54.4 here. And then we've done the same thing with the two other data sets here. We got those solid green squares here. That's going to be our data set, or our regression, our independent variable here, x3 here. And then I got this coefficient here. That's the slope of the data set here, or represents this line. This green line represents our data points here, those green squares here, and it has a certain slope here, 7.7 in this case. And then our other data, our independent variable, that's x1 here, and it's shown in this red line here. And those are the red squares that we have here. And that regression line here has a slope of 10.3 here. Just to point that out here. So we've done them separately here, those three different data points, to determine our y dependent variable here. Now, when we talk about linear regression, this is the case where we're going to be combining all three of these data sets here into one equation here. And this is what the equation is going to be here. I've got for our independent variable x1, it's going to have a slope here, 7.6 here. And if you look, it had initially, and what I'm showing here with these dash lines of the same color, that's after the regression here. So we have this slope of the line here. Before the regression was 10.3. Now it's going down to 7.6 after we combined all these three different data sets together and regressed them against our y dependent variable here. So just showing, get an idea what you're talking about when the slope of those lines changed here. So we are sitting at 10.3, now we're going down to 7.6. And that's for independent variable x1. Then we move over to x2 here, and we were sitting at, x2 was sitting here at 54.4. Now it moved down to 32.4 here. So you can see the slope of the line is decreased in all cases here. Again, those are those dashed lines here. And then for our x3 independent variable, we had 41 or 4.1 here, and that was sitting at 7.7 here, x3 here. Now, after we regressed it, the slope went down to 4.1 here, x3. Just to get an idea of what you're talking about. And we're going to be looking at, the question is here, this is the question we're looking at. Is the model better when all these x's are combined versus being separate, or just combining maybe independent variable x1 and x2, or maybe x1 and x3, or x2 and x3? Looking at maybe combining two of them. And then the equation we're going to be testing for here is this general equation here, our regression equation, where we combined all three of them here into one predictor. So for using through those three independent variables here, we can predict our y dependent variable here. Okay, so we just got an understanding what's going on when we're talking about multiple linear regression. When we talk about linear regression, we're setting determining a straight line that represents our different data sets here, and it's really the minimizing the sum of squares between those data sets to run a straight line. Okay, so that's for our looking at our XY graph here. Okay, so now let's go over here and let's look at it in terms of a 3 dimensions or a 3D space here. Okay, so again, we're going to have 3 dimensions, an x dimension here, a z dimension, and then that y predicting our y dependent variable here. These are, and just looking at it, in this case, I'm just looking at 12 different data points that we're going to be looking at. And they're suspended out here in 3D space here. And each one of those data points is defined by the x1, x2, and x3 independent variables. So they have 3 dimensions here, but they're going to have some weighted coefficients here, and each of the data points is defined by this line that we talked up over here. Okay, so that's sitting in 3D space. And then when we talk about multiple linear regression here, this is where we take and we regress, and we're going to look at those 3 different data points here, or those 3 different sets of points, and we're really coming up with a one slope here, where it's a combined slope. It's really what it's doing here is this. We're going through those data points and we're coming up with mean square average representing all those data points. So half of the data points here are below the line here, and then at least half of the distance here is above the line here. So we use a least squares linear fit here, looking at a 3D dimension, just to get a picture of what's going on here. Okay, so that's what we're doing. We're trying to fit a plane through those different data points when we talk about multiple linear regression here. Okay, so you can see it has a slope in your x direction here. I'm showing an x dimension here, and then it's got a scaling factor here, 0 to 80 in this case, and has a certain slope going up here. But then in our z direction here, our z dimension, it's got a different scaling factor here from 0 to 20, but it's got a steeper slope here going up here. And really, this equation here defines the different points on the line. And looking at any point on our coordinate here, we can predict our y dependent variable here based on the equation that we're looking at here. So that's what we're talking about when we talk about multiple linear regression here, where we're trying to fit a plane that's going through, in this case, those 12 different data points here, and we use the least squares method to do it. So this 3D space here, or drawing here, looking at 3 dimensions here, gives you an idea what you're talking about when we're talking about multiple linear regression. Okay, so now let's go on and and again, our y is showing here. We got a scaling factor on our y variable here, the dependent variable here. Y depends on those are 3 different, our equation here that's shown by x1, x2, and x3 here, just so you understand that. Okay, so now let's go on and let's look at our multicollinear model testing, or the tests that we'd have to do to determine whether or not we have a problem with the model that we're looking at here with those x1, x2, and x3 coefficients for each of those independent variables. Okay, now for our multicollinearity testing, and we'll be looking at a correlation matrix. Now this is where I've used Excel here, and under their data analysis, I've selected correlation here, and then under correlation I put in the different dependent and independent variables here. You could also be using equals correl here, and then you'd be looking at 2 different vectors here, comparing each of those different independent variables here. But what we're going to be looking at is just a correlation matrix where it combines all 3 of these, our y dependent variable here, and all 3 of those x independent variables, x1, x2, and x3 here. And with this multicollinearity, again, what you're testing for are all those independent variables correlated here. And the thing we have to look at here is when 2 or more of these independent variables really measure the same thing. What we're going to end up with large standard errors in our regression model here. Okay, so I've made my entries, and I've looked at, with the Excel, it would have given you our correlation matrix here, just to understand what's going on. So along our along our columns here in the top, I got the y-dependent x and x, x1, x2, and x3 here. And then along our column here, we're looking at x1, x2, and x3, and also our y-dependent variable here. So what we want to look at here, this is how this thing works here. So what we'd start out with our y-dependent variable here. This is where we're going to be looking at the correlation between x1, x2, and x3, shown in our column here. And what we want is really we need a high degree of correlation between our y-dependent variable and then all three of our independent variables here. So we're looking for a high degree of correlation, and you can see we do have in our correlation matrix, we're sitting at 0.72 or 72% here, 69.69 or 69%, and then down to 41% here. Okay, so that's for our y-dependent variable here correlated with our independent variables x here. And then this is what we want to look for with x1, x2, and x3 here. So looking at our x1 column here, move it across to our x2 independent variable, and you can see we have a correlation here of 0.39 here, or 39%. So sort of high correlation here, but nonetheless it's lower here than we had with our y-dependent variable. And then looking at x1 versus x3, we're down to 0.2 here, or 12%. Okay, and then correlation x2 here with x3 here, we're down to 31 or 0.31, 31%. So what we're looking at with our correlations between our dependent variables here, x1 and x2, with x2 here and x3, and x3 with itself, I'm just showing here at 1 here. Everything correlated with itself, you're going to see a 1 here, because perfect correlation with itself. So really what we want, we need a low degree here between our x independent variables here. And this is what each x is when they contribute to the recognition, our regression model here. That's what we're looking at. Each x is then contributing to the regression model as long as we have a low correlation between them here. If there's a high correlation between your x1 and x2 here, or x2 and x3, so forth, you're going to have, each of them are not contributing to the model, and then you're going to come up with those large standard errors. Okay, so in itself here, the correlation matrix answers the question if we got some multicollinearity here, and we might have a little bit here when we're talking about some of these higher values here. So really we want to go on and we want to check a bit further here. Okay, so moving over to our Excel, again, we're looking at an Excel output here, and we'll look at the regression statistics. So let's just start with our R-squared here. And what we've done, this is with all three of them here put together in this equation here that we were looking at here. So we look at our R-squared value, and we got a 0.75 here. That's 75%. Now, when I regress those separately here, x1, x2, and x3, each regressed against the y-dependent variable here. For x1, I had 52%, x2, 47%, x3, 17%. Now, R-squared always increases here when you add variables in here. So really what we have to look at, when you're looking at this regression, you also have to look at it, this adjusted R-squared here, and that's 0.66 or 66%. You have to get an understanding what that is here. Okay, so this is what you want to do. When you're looking for your adjusted R-squared here, we have the R-squared here. We want to see how this R-squared here affects our adjusted R-squared, because we've added, in this case, we added three independent variables here that we're looking at. So this is the question here. Check if your adjusted R-squared increases or decreases upon adding a variable here. So if it's increasing upon adding a variable, then we're good or better off here. But if it's decreasing as we add a variable, then we have problems here. So just to understand, and maybe the thing that you have to understand is just this basic equation here. Understand what your degrees of freedom is. So your R adjusted equals 1 minus your R squared. Here, that 0.75 here. And then you take that times n. In this case, we have 12 different data points that we have that we're looking at. N equals the number of observation minus 1. And then you divide that by n. And this is, again, number of different data points here. And then you would subtract from a k here. So you have to understand what k is here. K is really the different coefficients. We're looking at 3 different coefficients here for x1, x2, in x3 here. So that's a key point here. And then you subtract 1 from that. So take that fractional amount here, just so you understand your k and your n's here, times 1 minus r squared, and then you're going to come up with your r adjusted adjustment. So that's what the computer has done here. It's done it for you, but you have to understand what's going on if you want to really understand this here. So now, just comparing it, I did the x1 and x2, I regressed them together, and I come up with adjusted r squared here, 0.75 0.65 here. So we actually moved up a little bit here, 0.66 here. We didn't move down. So by adding our x3 variable here, we actually moved our adjusted r-squared up here a bit here. So maybe that's an indication that we're going in the right direction. Had we been sitting at had we gone down below 0.65 here, say we're down at 0.60 or something, then we'd be going in the wrong direction here. And adding that extra variable x3 here would not be the proper thing to do here. Then the other thing we want to check for is that our f-test here, and A over the f-test, and I just use, and the key point is here, again, you have to understand what you have to do to determine what your f-test is, your f-distribution is here. So again, with Excel, it equals f.inv here, .rt here, the right tail here. So what you have to do here, I'm using a 95% or a 5% test here. So you put in 0.05 here. The key is here, you have to know what degrees of freedom you put in here. So coming off, right off our table here, our regression, our explained sums of squares, you put that, we have a 3 here. And then our residual sums of squares is sitting at 8. So you put that into your equation or into your formula here, hit enter, and you're going to come up with an F score here or an F distribution here of 4.06 here. So laying that out on our F distribution scale here, looking at our 5% critical, then our point here is sitting at 4.06 here. So the key is here, now we've got our f-test here, and that's really taking your explained sums of squares here, that mean square, and you divide it by the residual sums of squares here, its mean square here. And you're going to come up with, in this case, our f-test is 0.837 here. So laying that out on our f-distribution curve, it's sitting here beyond, this is the key here, if your critical value is 4.06 here. So if you have an f-test that's below it, then you fail your test, then your r-squared is not viable here. But in our case, it's on the other side of our critical value, or 4.06. It's sitting at 8.37. So we passed our f-test here. So yes, our r-squared test here is good here, based on our ANOVA or our variance testing here. All right, so that's for our f-test here. But that doesn't tell us the whole thing here, this f-test. This is where we have to go down and we have to check our coefficients and our standard error through a t-statistic here. Okay, so what we've done, I've got the y-intercept here, and then we got those 3 different variables here, x1, x2, and x3 here, our independent variables here. Then it gave us some coefficient here for them. And then it kicks out a standard error here. So this is what's crucial here when we're looking at our model. That's what we talked about, that standard error and how we deal with that here. Okay, so you divide the computer here divides the standard error into the coefficient here, and it comes up with a t-statistics here. And you can see it for each of our variables. We got a t-statistic. And now we got to compare this t-statistic here against the t-distribution. It also has a p-value, a probability of being wrong here. Okay, so let's go down and let's look at our t-distribution here. And we got a two-tailed t-distribution here that we're looking at it in terms of Excel here. So what we have to do first here, we have to go into Excel here, and I'm using the t.inv here, .2t. And the key here is you have to know what your degrees of freedom is here. This is the key here. So in this case, we got those 3 different variables here. So our degrees of freedom that we're going to put in for our t-test, and we got 12 different observations. And because the k here, remember, we got 3 different degrees of freedom, 3 variables here, x1, x2, and x3. That's our k value. We subtract that. And then we got that one other degree of freedom here is really for that y-intercept here. So you always got that subtracting. So our degrees of freedom, what would we'd put in here? Well, we're looking at a 5% test here. And then our degrees of freedom after we do our arithmetic, we come up with 8 here. We have that k here, 3. And observations was 12. Hit the enter and you're going to come up with a t-statistic here, 2.30. So you lay that out on your distribution curve here. That's our 95% minus 2.30 plus 2.30 here. But this is where we end up in trouble here. Our statistic or r-squared looked pretty good, but now with looking at our t-stats here and comparing it to our our critical value here, 2.36 here, you can see the 2.8 here value, that's falling on the wrong side here. So for the 2.8, where this coefficient that we have, our x variable 2 here, is not very good because it didn't pass our 95% test. Now the t-stat here for the x variable 1 here, 2.8, really does, it's on the other side of our 2.36 here. So it marginally passes our test here. All right, so that's it. But looking at our variable 3 here, that x variable 3, it fails the test. It fails the test. We're only sitting at 1.9. I'm not showing it here, but it would be sitting up here. So you can see with this coefficient testing here, based on our t-stat and looking at those 3 different dependent variables that we combined here in a regression, we're ending up with some trouble here, especially x variable 2 here is marginally on the wrong side. It's not, and we got you can see the percentage here is 7% or 0.07 here is 7%. And then x variable 3 here, it's really bad here. You can be a 26% chance of being wrong with that, 7% chance for x variable 2, and 2% here for x variable 1 here. Okay, so I guess that pretty much looks at it, looks at our problem here and how we had to look at it. But just remember here, when we combine those different variables here, you have to look at the different, you have to look at your r squared, and then you have to go down, and even if that's good, then you have to go down here and you have to look at your different coefficients here based on your t-stat and lay out your t-distribution. Remember how to get your degrees of freedom here, because that's key here in order to determine your t-distribution here. Now, I could go and look at the case here where I just regressed x1 and x2 together here. And maybe we should go do and look at that here. Okay. Just going and looking at x variable here, x1 and x2. I did a t-stat on those here. I left x3 out here. And you can see our t-stat was 2.74 here and 2.47. Now if we go back over here on our t-distribution, you can see that there it is beyond our 2.3 here. So we were a little better off here had we just used x variable 1 and x variable 2 here. Had we just used those 2 different variables here to determine our y dependent variable, we'd be a little better off than adding our x variable 3 here. Again, it's marginal, but that's how you'd look at it here. Okay, so that pretty much goes through our discussion here with multicollinearity testing here, and you really have to look at that correlation matrix, and then when you go beyond that then you have to go beyond the correlation matrix, look at your r squared, your adjusted r squared here, see if they pass that F test, and then you have to further go on and look at the coefficients and the standard error here, looking at your coefficients here and your standard error for all of those variables here. And you're going to get, if you have, this is the key here, when you have you combined all those different independent variables to determine your dependent variable here, if things aren't going good, you're going to end up with large standard errors here, especially if the different independent variables here are correlated. And you can see we had somewhat of a problem here, and our model is not very good, especially with this x3, when we put that variable in, that independent variable into our regression model here. It ends up with some problems, and it also throws off our x1 and our x2 dependent variables as well. Okay, so that'll end our discussion.